Hello world, it's Craig. This is the second video on the design of this 8085 based STD Bus single board computer, and it isn't a video that I originally expected to make, but there's some updates on this design and I think there's some good lessons to be learned and some valuable information to share. So I'm going to slip this video in and save the aspects of the design that are required to be the STD compliant, which were the chips around the side, the drivers around the side. I'm going to save those for the next video. On my call in the last video to, let me know what you thought about the design and if you could find any mistakes. I received some very insightful feedback from viewers, and it's obvious there's some pretty deep knowledge out there. All of the comments were appreciated. Some were implemented, but even the ones that weren't implemented, it was a very good exercise to think about the suggestions. And I can say with confidence that there was not a bad idea among the many suggestions that were made to me. So remember, if you want to get in contact with me, there's an email on the SBC-85.com website. You can contact me, and I'll put a link to that down in the description. Of all the comments, Dennis in Australia wins the prize of the giveaway Prolog STD card, since he was not only the first, but he also found the biggest oversight in this design. And so this mistake pointed out by my new buddy Dennis would have severely limited the flexibility of the memory mapping, and it can be summarized as follows. In certain configurations, the switches can result in an inadvertent cross-connecting between the default and the swap memory switches, and that cross-connecting would then allow simultaneous enabling of multiple memory devices. So if that tells you enough, if as soon as Dennis mentioned it to me, I said, ooh, yeah, that's exactly right. So if that tells you all you need to know, you can skip ahead a few minutes in the video. But if you want a more detailed description, then stick with me while I do a quick KiCad demonstration of this area to highlight what the problem is. This is the original design, and in this design, under certain memory mapping configurations, the switches set for the default map could interfere with the swap map. In fact, it would happen any time that an 8K block of the default configuration crosses a boundary of a device that's set up in the swap configuration. And this becomes more and more likely the more asymmetric the memory blocks in the default and swap maps become. Rather than try to talk through the explanation, it's easier to just show you. I'm going to use KiCad as a little simulation tool. As I mentioned in one of my reverse engineering videos, KiCad, you can wire things together and short wires, but KiCad doesn't really care if you wire them. All it really cares about is if they're connected to the same net. And rather than wire them, another way to connect them into the same net is just give them the same net name. Right now I have the highlight net selected, and I can highlight one of the lines coming out of the decoder, and all I'm doing is highlighting what's connected to that net. And you can see the lines turning purple or magenta, whatever color that is. So with nothing force connected, meaning no switches are closed, I click on these and I kind of pseudo enable each of these decoder outputs, and the main line and the switch inputs for each are highlighted. Now I have some labels here. They're just sitting in a pile, so they're not connected to anything. These are the M1D pile, and that stands for memory 1 device default. I'm going to take those and I'm going to simulate closing this first switch, because now I have the M1D net name on the common for the switch and also on switch 1. So now if I select that input, you can see that this input would go low, would come in switch 1 is closed, and so it would come out switch 9. Now everybody that's connected to that would be low. Let me go ahead and set up 16K memory block on this for the default and for the swap. And I can go through, check these one at a time, and I can see that, okay, that's what would be highlighted if either the first two are low, nothing for 3, 4, 5, 6. If I do either of the last two, then these guys are highlighted. Okay, so that works just as expected. Now, obviously, we're not actually simulating any logic here. It's just showing us what is electronically connected together, and even that we're forcing it to show us. So we're just using it, so it's not really a simulator. There's no magic here. We're just forcing these connections, and it's highlighting what would be connected at the same time. So I'm going to finish this one up. I've got 16K highlighted on this first device at the bottom and 16K at the top. I'm now going to expand that, so I'm going to have 32K at the bottom and the top, and I'm going to put in the second device. So let me go ahead and set those up. Now it's set up. I've zoomed out a little bit so we can see the decoder lines, and we can also see the multiplexer at the bottom. And the key thing is at any one time we should only have one swap and one default selected, because if there is more than one selected at a time down here on the multiplexer, that means that more than one of these devices out here would get selected. So let's go ahead and look at the decoder. I've got, as I said, 32K for the default on the bottom, 32K on the top, and then I have 24K of the M2 at the top for the default and on the bottom for the swap. And if I select any of these first 4 lines of the decoder, you can see all of those go low because those are coming in. They're all shorted together in this switch 1. So for the first 4, any of those first 4 lines are going to select all of those, and any of the 4 high bits are going to select the swap. But if we look down here at the bottom, we can see that selecting any of the first group or the second group, I've only got one default and one swap selected. So this is working as, original plan, and this is kind of what I had in my mind when I set this up. But now let's look at what the problem is. The problem is that if I reconfigure this second socket, so rather than being at the bottom, let me move it so it is at the middle. So this will highlight the problem. Anytime something is selected across a boundary of another device, it just completely screws up the whole system. So now I've got these 4 on the bottom, these 4 on the top, but for the M2 device, for the default it's at the top, but for the swap it's in the middle. And so what we see now is if we select any of these lines, these 3 that are shorted across the middle basically are shorting these 4 from the bottom to these 4 from the top. So no matter which encoder I select, everybody lights up. So now I've got 2 swap and 2 defaults enabled at the same time. So obviously that would, if I had selected the default, that would be selecting both of those guys, both the M1 and the M2 at the same time. So a great thank you to Dennis for pointing that out. I have a Prolog card here for Dennis that literally has his name on it. Here, my little asset tag. It's got his name written on it. This is a Prolog 7805. It's their second version of the 8085 CPU card. So this is going to Dennis as soon as we can get a cost-effective way of getting this thing to Australia. And while I'm talking about that, Dennis also pointed out that I don't know if you have used the Max 232 in your circuit in KiCad, but whoever drew that symbol for the Max 232, they made it like 5 times bigger than any other symbol. So finally, after that irritating me for years, I finally decided to redraw it. I redrew it, I scaled it down so it was a decent size. I moved the pins around so I can kind of take some shortcuts in wiring it up. And in doing all of that, I forgot to flip C12. So in this diagram, C12 is backwards because the VS Plus on pin 2 is actually higher than 5 volts. So when I finally made that a decent size, and then I screwed it up. So, I don't know, has getting COVID made anybody else just feel significantly more stupid? I don't know if I'm just more stupid or if I'm more stupid and I'm more lazy or careless about going back and checking things. I used to go back and double check everything, but now I just do it and I say, yeah, it's good enough. So, either way, I'm certainly glad that I'm over the hill, so very little is expected of me at this point, but I would really hate to be at the prime of my career and, dealing with some of these lingering effects of COVID. So I'm going to blame that mistake on carelessness of having COVID. So back to the decoder, Dennis wasn't one to just point out a problem. Dennis also suggested a solution, and I couldn't think of a better solution, so I adopted his. Let me flip over to the corrected schematic. So this is the new schematic, and Dennis's solution was to simply add a second decoder and remove the multiplexer. So I've got two 74-156s now. Both of them are using the same A13, 14, and 15 to decode their outputs. So based on those 3 values, they're going to decode the value. But one of these is just for the default. So we've got an enable coming in here that is the default active low enable. And then we have another one, which is just the invert of that, which is an active low swap enable. So basically, these 2 decoders are now going to take turns being enabled rather than multiplexing it afterwards. So we're essentially multiplexing it beforehand rather than afterwards. And now the outputs of these switches, so before we had the output on pin 9 going down to the multiplexer, now the output of these switches can just be connected together. And at first I thought that I would need to AND those two together to keep them isolated, but I believe that I've worked through it, and you can see there's a little pile of labels here that I played the same game that I just showed you with the other one on this version, and I think I'm okay having those connected together because, in a properly configured system, now only one device is going to be connected to any single decoder output line, where before I had two devices connected to the same decoder line. Now, at most, one device is going to be connected to that decoder line. So these don't have to be isolated. They can just be shorted together. Output of these switches then goes down into the OR gates along with the IOM, just like they did before. So no more chips. I just swapped out that one multiplexer for another decoder. And in fact, before I had to have an 8 resistor pack here, now this dropped down to a 4. So actually it saved me 4 resistors on the board. Much improved design. Really appreciate Dennis's input on that. So hopefully the decoding scheme is going to work as I originally intended. And if you see a problem with that, let me know before this thing goes to the shop. There's a couple of other things that I did change on this board while I was changing things. And one of them is the reset. I got to looking at the reset and I decided to put that supervisory in this to prevent the CPU from getting some false starts as the power rails come up. I doubt that anybody's going to be using this on a giant 24 card rack. But if they do, the power rails can be a bit dodgy when they come up and when they go away. So I added this microchip power supervisor. It's the MCP 120. It's just an open drain output, and it will clamp the reset to ground until the power is clean when it's coming up. So it holds the reset line low for 350 milliseconds once the 5-volt rail gets to its trip voltage. And on this is the MCP 120 485. So once the voltage gets to 4.85 volts, this will wait 350 milliseconds and then it will release that reset and let it float up. Likewise, on the way down, about 10 microseconds after the rail falls below that 4.85 volts on that supervisory, it will pull that reset line low. So it'll catch it on the way down just as easily as it holds it off on the way up. So that 350 milliseconds is plenty of time for that 8085 to get in, the 3 or 4 or 5, whatever T-states it needs to have while the power is up, before the reset is released. I had a little conversation with Ian down in California about a couple of diodes. And let's look at this one down here on the speaker first. Now, after we discussed this, I told Ian, I'm going to buy into that. I'm going to put these diodes in. But when I actually started looking to see where I'm going to put it on the circuit board, I may actually leave these off because I don't think either one of them is actually critical. The first one is this freewheeling diode across the speaker. Now, I've used this little speaker being directly driven from logic gates a lot. I haven't had any problem with it, but I could be convinced that this freewheeling diode is important, particularly if somebody uses a larger speaker or if they decided that instead of a speaker, they wanted to put in a little relay here, or a little relay or something has more inductance than just that little speaker. Now, the idea of a freewheeling diode, of course, is it allows the current in the inductive load to decay naturally rather than try to stop it with the controlling device. So if it weren't for that freewheeling diode, if I have this speaker energized, I've got current going through the speaker. Now if the 74 LSO4 wants to shut this off, it has to absorb all of that inductive current that's being driven into its output. But with the freewheeling diode there, the 74 LSO4 can just shut off, and this current then will go through that freewheeling diode until it naturally decays through the resistance of that speaker. As I said, with this little CVS 1508 speaker, I haven't had a problem with that. But if somebody wanted to use a bigger speaker or a relay, that freewheeling diode would be important. Now, this is in the scratch pad area, the little sandbox. So it'd be easy for somebody to put their own diode in, but it wouldn't hurt to have the markings on the circuit board that if somebody wanted to use something that was more inductive, to have a place for that freewheeling diode, and any switching diode will work. The second diode is on the reset. And again, this one I don't think is necessary primarily because of the supervisory circuit. But if you look at a lot of schematics for microprocessors, and the reset will have this diode in it. And the diode goes from the reset up to the 5-volt rail. And at first glance, it looks like this diode isn't doing anything. But processors need a good clean reset after the power comes up, or they can lock up. And the Z80 is especially prone to that. The 8085 not so much. But if we look at this reset circuit, we use this simple RC to take care of that. Here's this 1 microfarad down here that's charged up with this 75K. So that 75K slowly brings the active low reset line to logic 1 and takes this out of reset. And on the 8085, that's Schmidt triggered, so it's usually a fairly clean reset. It might get a couple of resets in, a couple of instructions, but it'll usually a fairly clean reset. Now, the push button reset here just shorts the capacitor out back down to ground to discharge it, and then to kind of soften the surprise, I put in this 1K that the charge from the capacitor is actually drained through. So you push the button, the reset line goes low, you let go of the button, the capacitor has to recharge again by the 75K before the processor can start again. So that's all fine. Question is, what is this extra diode that you see in the data books? And that diode is actually an early trigger for when the power supply turns off. So it has nothing to do with the power supplies turning on. It's for when the power supply is turning off. So if you get a power fail and the 5-volt rail starts going down, there'll be a period of time when some parts of the board have power, some parts don't. Some things will start to misbehave in such a way that outputs can start changing in unfortunate or dangerous ways, and data can become corrupt. So the purpose of this diode is to become an early warning that as soon as the 5-volt rail starts to go down, this diode will quickly drain the capacitor and put the processor into reset. So that more cleanly will put the processor into a reset on a power fail. So while you see that diode in the system reset in many textbooks and data sheets, most of the time they don't tell you the purpose of it, but now you know that's what that diode is for. But since the supervisory circuit will pull the reset low within 10 microseconds of the rail going below that 4.85 volts, it'll catch the power fail long before this reset diode knows what's happening or what's going on. So if I have room, I may leave a place for it on the board. It's up to the user if they want to install the diode or even the supervisory IC for that matter. I think one or the other would be fine. Neither is really critical, so it'll depend on what you have sitting around or if you want to spend the 4 or 6 bits or whatever that supervisory circuit costs. There is one more change that I'm debating on this board, and that is down here on the system reset line. If we look at the bus, the system reset is on pin 47 of the bus. And in the WinSystems catalog that I showed you earlier, last video, where they're talking about the signals for the STD bus, in that catalog, they call that out as being open collector. And I don't remember that being open collector before, but they called it out as open collector. I don't know if that was a late change or what. But the idea is that other cards in the system may want to pull that system reset low. So whoever is driving it should make that open collector so that somebody else can pull it low. And I guess I came to age with the idea that only the master processor should be pulling that system reset low, and so I didn't think that the master processor should have to have that open collector. And I went back and I looked at the processor cards I have from the two creators of STD. I looked at my Prolog and my MOSTEC cards, and to see if they had this driven as open collector. And they have the signal coming out of 74LS, like a 240 or 244, 245. They have it coming just directly out of that chip and going to that finger on the bus. So they do not have that as open collector. But rather than put in an open collector device for this, I could put in a little, an 8-pin, 2-bit open collector device to buffer that and make it open collector. But I think what I'm going to do is just put in a place for a germanium or a Schottky diode that you can wire and this line, which will protect the output of this 74LS244. So normally this pin 18, before I just had it connected right into that bus reset, if we put that diode in, now that pin 18 can only pull that line low. There's enough pull up over here. There's a 4.7K that'll pull that line up. And so it's okay for this 74LS244 to just pull that line low. Now, if somebody else wants to pull it low while that 244 has pin 18 high, it's not going to hurt anything. Of course, we do have the voltage drop across that diode, but if it's a germanium, we should still be below the threshold voltage of that logic 1. So that should still be recognized as a logic 0 when we pull that low. But if somebody feels strongly about that, they don't like that germanium diode, they can just short that out. And there is an open collector version of the 244. It's way up in the 700s, the 760 or something like that, which is an open collector version of that 244. So if you feel strongly about it, you can just put that in instead of that 244. But personally, I don't feel that strongly about it. I don't think anybody else should be pulling this system reset low. Maybe you'll have a card that is pulling it low. If you do have a card that pulls it low, I'd really like to know. But I really think that the only thing that should be pulling it low would be a watchdog. And even the watchdog, I think the watchdog should pull the push button reset on pin 48 low rather than that system reset. I think the system reset should be reserved for the master controller. All right, I think that pretty much captures the changes in the design since the last video. As I said, I want to go ahead and wrap this up, get these off to the shop. I have another project I'm excited to show you. I think I'll be back on track for the next video, so that will be about the signals on the board that are required to make it STD Bus compliant, and hopefully I can get that video done before too long. As always, this channel is fueled by likes, engaging comments, subscribers, and shares, and I really appreciate the feedback I got from the last video on potential changes to this board. They were very, very useful. That's it for today. I will talk with you later. Thanks again for watching. Bye-bye.